Let me see. There we go. Mm, 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 mm. Let's see. Looking for a good definition. Just like this first. All right. So when we look at derivatives as a rate of change, they start off talking about displacement, which is going to get us into velocity, speed, acceleration, and jerk. I should have mentioned, that's why I did this in purple, the position S. S doesn't represent speed in physics, it represents position. So position S on the line as the function of T, we're going to be calling it S, and we'll have a function for each different position. You'll see what we're talking about when I actually get a formula. But S will represent your position. So displacement is the movement of an object along a coordinate line. When you implement the change in S, delta, whenever you have delta in front of a variable, that's the change in that variable. That's Greek letter delta. All right. Oh man, oh, you're writing in. I have my eraser on.
Of position with what?
Respect to time.
Okay.
Yeah. So velocity is going to be the derivative of position with respect to time. So that means v of t. So that s, whatever s is, the formula for your position, we would take the derivative of that, and that will be your velocity. And so your velocity is how fast an object is moving along the horizontal line. So speed measures the rate of progress regardless of direction. It is the absolute value of velocity. All right, so acceleration is the rate at which a body's velocity changes. So it measures how quickly the body picks up or loses speed. It is the derivative of velocity. So, so it's the derivative of velocity, which is the second derivative of position. Last one, and then we'll do a problem or two. Jerk is all right. So jerk is a sudden change in acceleration. It's the derivative of acceleration, and that means it's also the third derivative of position. All right, so let's put this to work. Let me see.
Is that in a free fall?
That is a free fall, ma'am.
Okay.
Sorry, man. Sometimes I get lazy with this writing. So it says in a free fall of a heavy ball bearing, release from rest at t equals 0 seconds. All right. A. All right. So in a free fall of a heavy ball bearing released from rest at t equal to 0 seconds, first question is how many meters does the ball fall in the first 3 seconds? So write this. All right, so the metric free fall equation is S sub t, or S of t, not sub t, but S of t equal to 4.9 t squared. And so the formulas and the equations, they should be giving those to you in the example or in the problem. There's some place, some spot. So if you want to know where the ball would be located in the first 3 seconds, and all you would do is plug in 3 to the equation. 4.9 times 3 squared. This should be 44.1 meters. Any problems with that? I think that part's pretty much straightforward.
I don't have a problem. I just have a question about it. Is it
Yep.
just a known fact that things fall at 4.9 meters per second squared?
Yeah, that's just going to be the formula for the free fall. Yep. And there's another position equation as well. Your conditions will dictate what formula you use. So the fact that it said free fall lets you know you would be using this equation and stuff. So, well, like I said, it was given. Let me see. Dynamite blast, blow heavy rock straight and reach the height. Yeah, so then they'll give us another one in the next example. So it just depends on what's going on. The more you dive into physics, the more you get the specifics on which formula to use when. Uh, so what is the velocity, speed, and acceleration at t equal to 3 seconds? All right. So your velocity is going to be derivative of s. So just write in different notation. Remember, s prime means the first derivative of s. So taking the derivative of 4.9 t squared, that's 4.9. Bring your t down. Subtract your exponent. Subtract 1 from your exponent. So that's going to be 9.8 t. That's your velocity. And then you will plug in 3. That should be, whoa. 29.4 meters per second.
Where did the 4.9 times 2t come from?
When you do the derivative of 4.9 t squared, you bring your 2 from your exponent down front.
That's right. Yep. All right.
Yep. All right. So that's our velocity. And I probably should have wrote something along those lines. Speed, it's just the absolute value. Yeah, no shortcut there, just write it. Absolute value of V3, which is 29.4 meters per second. And what we're doing, acceleration. Next. And don't forget that's the derivative of velocity, which is the second derivative of your position. And so we're looking at the derivative of 29.4. No. No, it's the 9. Where'd it go? 9.8t. Yeah. Sorry about that. Derivative of 9.8t with respect to t. That would just be 9.8. And because there's no t, once you take the derivative here, the t is going to disappear. Because remember what happened before, we brought down the exponent. So the exponent is 1 right here. Bring down 1, then subtract 1 from it. You'll have 0 as your exponent. So this will just be seconds squared. So that's your measurement and acceleration. It's your measurement and speed, and then velocity as well. So you notice you're going meters per second, and then acceleration is meters per second squared. Let me check this problem. How you guys are finishing up? see something else in the text. All right. Questions so far?
Can you run over how you got the answer to the acceleration one more time?
Yeah. So when you do the derivative, so the first thing we had to do was the derivative, or take the derivative of 9.8t over, with respect to t. So now let's say if that was 9.8t to the third power. The way we would do it is the 9.8 will still be there. You bring down your exponent and then subtract 1 from it. So that would be 9.8 times 3t to the second power. And then you would do 9.8 times 3. And that would be 29.4 t to the second power. So that's how you would do it. Now, we didn't have that. We just had t to the first power. But that process still holds true. Our exponent is 1. So we're going to bring that down front and then subtract 1 from it. So what's going to happen is we're going to have 9.8 times 1t and 1 minus 1 for your exponent. 9.8 times 1 is 9.8. T to the 0 power, because 1 minus 1. And anything to the 0 power is 1. So that's how we just have 9.8. All right. Questions, any questions? All right, so
No
let's,
questions.
all right, cool. Thank you. Let's do at least one more. Let's see what this problem talks about. A dynamite. Oh, straight up. I missed that all up. All right. So a dynamite blast blows a heavy rock straight up with a launch velocity of 160 feet per second. It's about 109 miles per hour. It reaches a height of S equal to 160t minus 16t squared after t seconds. 160t minus t squared feet after t seconds. So I'll scroll up a little. First question is, how high does the rock go? So it's shot up into the air at a velocity of 160 feet per second. So if you think about it, the rock is going up into the air straight up, and at some point it's going to stop with its velocity and come down. Right? So even if it goes straight up, and then comes straight back down, it has to go up, and then its velocity has to stop at a point, and then it starts to come down. So we want to know, it says, how high does a rock go? We want to know, when is the velocity? Basically, the question is saying, when is the velocity equal to 0? All right. Once the velocity equals 0, then it'll stop going up and begin coming down. So that's the highest that it would go. So we have our position formula, but we need velocity. So we need to take the derivative of the position formula. In order to calculate the velocity. That would be 160 minus 16 times 2t. All right. So that's your velocity formula. So once again, don't forget, whenever you're dealing with just your regular exponents, to take the derivative of it, you're going to bring your exponent down and then subtract 1 from it up top. So we brought 2 down front, and then we subtracted 1 from it up here. So that's why we have 1 as an exponent and then 2 right here. All right, so now we set 160 minus 32t equal to 0. Solve for t. So it will reach its height. And let me make sure it says, oh, well, we know that it reaches height at 5 seconds. So that's not the answer. Just, it's going to help us get there. It's going to reach its height at 5 seconds. So it's going to reach its height at 5 seconds, but it didn't ask us at what time will it reach its height. It actually asked us, let's go back, how high does the rock go? So we need to take the position formula, which is 160t minus 16t squared. I think I got all that in there. 160t minus t, 16t squared, yep. And then plug in 5 to see how many feet it goes into the air. All right. Questions on that? All right. Questions before we look at the next, or another question dealing with the same example? Okay. B. All right. So what are the velocity and speed of the rock when it is 256 feet above ground on the way up and on the way down? So don't forget what's actually going on here. We have a parabola. You know, it might not be that fat, but we do have a parabola, and we have this marker of 256 feet. So it's going to hit 256 feet on the way up, and then it's going to hit 256 feet on the way down. So don't forget 256 feet relates to your positioning and the position formula. So first we got to find the times that it actually hit 256. And we got to use the position formula in order to do that. So we want to know when is SOT 160 T minus 16T squared. When is it equal to 256? All right, so we need to set one side equal to 0. I always go ahead and take these over since my leading coefficient is negative. So I'll add 16t to both sides, subtract 160t from both sides. So I'm looking at positive 16t minus 160t plus 256 equal to 0. That's 16 times 16. Yep. So took that trinomial and factored it, pulled the GCF out just to make things a little easier. 16 went into all three terms. So once you do that, you can factor into your two binomials of t minus 8 times t minus 2. T equal to 8 seconds will be for the first one, and then 2 seconds for the second one. So on the way up, it hit 256 at 2 seconds. On the way down, it hit 256 at 8 seconds. All right. So now we want to know what is the velocity at the time. I think that's what we were asking. Let's go back to make sure. Yeah, what is the velocity and speed? So we know speed is just the absolute value of the velocity. So we'll take the velocity formula, which is 160 minus 32t, if I'm not mistaken. I'm trying to remember it. Let me just go back to make sure. Yep, 160 minus 32t. So we plug in 8, plug in 2. So velocity at 8 seconds. Notice it's negative because that means it's on the way down. Velocity has direction. Positive at 2 seconds because it was on its way up. And then the speed, remember we said is the absolute value.
Will that always be the case, or is that just a coincidence that it's going the same speed up as it goes down?
It's going to be the case for this type of problem because, right, you're going up and down, and, you know, it's a parabola. So it's meeting at the same spot at 256. That's going to be a horizontal line at 256. So in order for it to be something different, something funky has to be going on. But if it goes up at that speed, it's going to come down like that, at the same spot. Didn't you do that? All right, almost finished. C is what is the acceleration. So what is the acceleration of a rock at any time after the blast? So you would take the derivative of your velocity. Hold up, let me make sure I got it. It's 160.32t, right? Don't forget the derivative of a constant goes to 0. So basically, yeah. And since there is no t, I'm gonna do like not do it like this. So since there's no variable t, and I can write this note too. Oh, excuse me.
Would there be a way to calculate the deceleration of the rock?
All right, so the deceleration. So let me see, deceleration of the rock, because we know the effect of. I'm trying to see and trying to think. Is there a, let me check on the difference. Trying to think. So acceleration is always downward because of the effect of gravity on the rock. The rock rises, it slows down. And because I'm trying to think, is that just, you know, is acceleration and deceleration? As a matter of fact, let me look at something real quick since you asked. Mm-mm-mm. Yeah. So deceleration always refers to acceleration in the direction opposite of the direction of the velocity. So deceleration and acceleration are the same. So, so the velocity is going up, it's taking it up as it blows as the blast takes the object up. The deceleration is what's acting or slowing down the velocity. But then as the acceleration, which is what we're calling deceleration, is what slows down the velocity. Then as it goes down, then that's just considered acceleration. So acceleration and deceleration are the same thing. So the negative um, is a representation of the deceleration. All right. And I think there was one more, and then we'll be done. All right, last one. So when does the rock hit the ground again? All right. So we go back to our position formula, and that was 160t minus 16t squared. And we want to know when is when is position 0. So, and I can write that. So we know it's 0 initially. And so we want to know when is it going to be 0 again. That's what you're talking about hitting the ground. So we take our formula, set it equal to 0 and solve. Once again, we can factor out 16. We factor out 16t this time. Set each piece equal to 0. Divide by 16, t is equal to 0, which is the one we know about. Then if we were to add t to both sides, t is equal to 10. So this is initial position. Uh,
Can you scroll up a little bit?
Yep, give me 1 second. Write that down. So it hits the ground at 10 seconds. Tell me where to stop.
You're good. You can scroll back down. Sorry.
Okay. Oh, no, you're fine. All right. So, try that out. I'll post that homework, I guess, tonight. Try it out when you get a chance. I know you guys got stuff going on, so I understand. So there's no due date on anything right now. So just see if any questions pop up, and if we need to rehash something or go over something else, or go over it again, just let me know. So yep. Any questions or concerns before we close out? All right. Well, I will. What I'm gonna do, and I can't believe I haven't done it up to this point. I don't think I've recorded any of our sessions, but I'm gonna try to record the sessions from this point forward and shoot them to you guys, so that if you wanted to review the lecture, then you could. So this will be the first one of our recorded lectures. So yep. Let me know if you have any questions, and you guys have a great weekend.
Thank you.
All right.
Bye.
Thank you. Have a good one.
You
Bye.
too.